Welcome back. Let's discuss how improved momentum can stabilize the performance. If you haven't watched my previous momentum video, I highly suggest please watch that and then come back here. In the previous momentum video, we discussed the main idea behind momentum, that if for few iterations, if the gradients point in the same direction, then we'll take much larger step in that direction. So we came up with this kind of formula here. So for normal gradient descent, we had this equations, right? Wt equals to Wt minus 1 minus alpha times the gradient. So if we have gradient is same for multiple iteration, right? G hat W0 equals to G hat W1 equals to G hat W2 and so on. So on all are, let's say, G hat, right? So in this case, if all the gradients are same, even in that case, for normal gradient descent, we'll just subtract minus alpha G hat from the previous weights, and that's how we update the weight. So in case of gradient descent with momentum, Wt equals to Wt minus 1 plus Vt, or Vt here is this thing. So minus alpha G hat divided by 1 minus beta. So I highly suggest please go through the previous momentum video first to get the understanding. So here what happens is this, we get one extra term, right? So earlier we just had minus alpha G hat and now we have 1 over 1 minus beta. This extra amplification factor we are getting. If beta is between 0 and 1, then 1 over 1 minus beta is much larger value, right? So that's why we are taking much larger steps in the direction. So here in this video, we'll take a different approach of momentum and we'll see how it is better. So in the previous video, we also talked about few limitations, like one limitations of momentum. So let's say this is one 2D loss curve, and if we are moving, let's say, in this direction, if we are taking much larger steps, so then it's possible that we overshoot the minima. We reach here, and from here to here, and from here to here, then from here to here, right? So this can oscillate, and it will not converge. It might not converge. So we'll try to tackle this problem little bit here. So for that we use convex combination. So this is not as complicated as it looks. This is very simple concept. So convex combination of x and y is beta x plus 1 minus beta times y. So let's say if beta is between 0 and 1, so this value will always lie between x and y. How? Let's say this is x and this is y, right? So what we are claiming is this value will always be within x and y. If beta equals to 0, we get 0 times x plus 1 minus 0 times y. So that means y. If beta is 1, we get x plus 1 minus 1 times 0, that is 0 times y. So that is we get x. So beta is ranging from 0 to 1. So for 0 and 1, we get x is the minimum value, y is the maximum value. If beta is half, we get half x plus half y. So x plus y divided by 2. So this is convex combination for two variables. So that's the concept we are going to use for this momentum approach. So earlier we discussed about this momentum formula, right? So Vt plus 1 equals to beta times Vt minus alpha G hat of Wt. So here what we are doing is, here this Vt plus 1 or Vt, so this is the velocity or the gradient accumulator, right? So this is a convex combination of Vt and G hat Wt. So Vt is the gradient accumulator and G hat Wt is the gradient in the last iteration. Now in stochastic or mini batch gradient descent, gradients can change direction due to different batches. So in batch gradient descent, we consider whole data set at a time, but in stochastic or mini batch gradation, we have multiple batches, right? So batch 1 might have gradient going up, batch 2 have gradient going down, batch 3 might have gradient slightly up. So we can have different directions for different batches. So if you take a convex combination, it averages these gradients, so making the update little smoother. So the result, what we get, less zigzag update and more stable path to minimum. So we have seen the contour plot, right? So contour plot means different in a loss curve in 3D, and I can't show the 3D in here. So if we convert it into 2D, we get the contour plot, right? So similar color points represent the same height. So let's say you are starting here. Let's say you are starting here. So it will take much smoother path till to reach the minimum. Now see one scenario. So let's say G hat W0, the gradient at the first iteration or 0th iteration is minus G1 minus G2. This is the gradient vector. At second iteration or at the first iteration, G hat of W1 is minus G1 G2. So this gradient vector, these are different directions, right? So in this direction, in the first row, if you consider, gradient is remaining same in this direction. But in this direction, for the second row, you see gradient is changing in this direction. The gradient direction is changing. So let's compute this V0 velocity here. V0, let's say we are starting with 0. So V1 using this formula will get 1 minus beta times G hat W0. G hat W0 is this. So 1 minus beta times this. V2 is what? Using this formula, beta times V1 plus 1 minus beta times G hat W1. V1 we got here, that is beta times this whole thing 1 minus beta and this vector minus G1 minus G2 plus 1 minus beta times G hat of W1. G hat of W1 is this minus G1 G2. Now we got this. Let's simplify this little bit. So, and for the first row, if you see minus G1, all the gradient is pointing in the same direction. So, we get beta minus beta square plus 1 minus beta times minus G1. For the second row, we have minus G2 here and G2 here. So, let's consider this minus, take this minus here. We get minus beta plus beta square plus 1 minus beta times Z2. So what this beta and beta will cancel out, right? So we get 1 minus beta square here times minus G1. And here in the second row, 1 minus 2 beta plus beta square times Z2, which is what? 1 minus beta whole square, right? So we get 1 minus beta whole square times Z2. So this we are getting the velocity V2 for second iteration. Now, this way, if we keep computing, right, if calculating, so this we can be derived for tth update. So Vt is beta times Vt minus 1 plus 1 minus beta times G hat Wt minus 1 using this formula. This can be proved, this can be shown that it will be like 1 minus beta power t times minus G1. And in the second row, we'll have 1 minus beta whole thing powered by t G2. So this is for tth update. This can be derived. Now to understand the maximum possible velocity, right? So we'll compute the limit. So this we got for the tth update, but to understand the maximum possible velocity possible. So let's say beta is always 0, between 0 and 1, right? So limit of beta power t, where t tends to infinity, will always be 0. So let's just quick intuition, right? So if you take 0.5, if you compute the power, right, 0.5 square, we get 0.25. Again you square, we get it much lesser value. So if beta is between 0 and 1, beta power t will always tend to 0. So limit of 1 minus beta power t will be 1 when t tends to infinity, and limit of 1 minus beta whole thing powered by t. So beta is between 0 to 1, between 0 and 1, right? So 1 minus beta also will be between 0 and 1. So limit of this power t times is also 0. So this thing 1 minus b power t, this thing is maximum value possible is 1, and for this things 1 minus beta whole thing powered by t, so this is will be maximum value is 0. So what we are getting here is, so the gradient in this direction, so gradient in the first direction, gradients were same, right? So in the g hat of w0 we see minus u1 minus u1. So gradients are same in the first direction. In this case we are getting 1. So in the second row, for the second row, gradients are not same. So it is taking different direction. So minus g2 and g2, that means totally different direction. So it is tending towards 0. So if gradients are consistent in some direction, then we'll take large step in that direction. If gradients are not consistent, inconsistent in some direction, then we'll not take large step in that direction. So that's the main agenda or idea behind momentum, right? So now here you see, right, in blue we have the gradient descent without momentum, like it is not a very noisy path, and here in red we have gradient descent with momentum. So you see it's much smoother path. So here in horizontal direction, gradient is consistent. So we are moving towards this minimum, right? But in vertical direction, gradients are not consistent. So will be taking larger step in horizontal direction, but smaller steps in the vertical direction with momentum. Now, then this approach, the convex combination form of momentum, creates a stable exponential moving average for gradients. So, what it helps with, will have it smooths noisy updates. It reduces the oscillations around minimum that we already discussed earlier, accelerates learning in consistent directions, and it stabilizes the optimization.